So, myself is K Nandi. I am from IIT Kharagpur in the department, rather center, not department, Cryogenic Engineering Center. I believe many of you may not be from cryogenic background. So, let me explain what is cryogenics, and then main topic is on heat exchanger. Then in cryogenics, how these heat exchangers are considered or talked about. Cryogenics means basically if you talk of any activity less than or below minus 150 degrees centigrade. You know, in fridges or refrigerators, in household refrigerators, we talk of minus 5 degree, minus 10 degree centigrade. But if you go for cryogenic temperature, the temperature is minus 150 degree centigrade. This is a workshop, so I feel that I should go very slow so that you can understand a bit of it, which is really, that will be of my satisfaction if you understand it. Now, what happens that at this very low temperature, as you know that temperature is low means minus 150 degrees centigrade and your room temperature is 300 degrees centigrade. Obviously, the issues, there are many issues because of this large temperature difference, 300 degrees centigrade and minus 150 degrees centigrade. You know, then immediately your question may come, what is this, how do we get this such a low temperature? Excuse me sir, can I? Please, huh? Okay. So this is introduction part I am talking on. So if I am not able to present myself before you, or if I am not able to introduce myself properly to you, that I cannot talk properly in the topic itself. Now what I am saying that, you know, immediately the next question will come to you, that how do you create this such a low temperature and what is all about. To be very in layman's view, I will say that as you see water, as you heat it, you get steam out of it. Or in other words also, if reduce the temperature of water, you can get ice, that is the solid, liquid and the vapor. Now, the air what we feel around us is of gaseous state. Now, same as water, if you reduce the temperature of air, you will get liquid air, and that liquid air temperature is below is 77 Kelvin, near 77 Kelvin or 80 Kelvin around, which is about minus 200 or 193 or so Kelvin degree centigrade. Now, this is maybe liquid air, liquid oxygen, liquid nitrogen, liquid argon, liquid helium, liquid hydrogen, liquid methane, liquid neon. All these so-called permanent gases, what we think they come under in the liquid form, they come under the gamut of cryogenic engineering. Now, in cryogenic engineering, there are several applications of low temperatures. To name a few, maybe rocket propulsion, and then liquid nitrogen is plenty of used anywhere, many places. Now the question is that in all cases you have to have some kind of heat exchanging device. That means you have to exchange heat between hot fluid to the cold fluid so that you get the desired performance in the other stream. Okay, desired requirement for the other stream. Now let us see, then in this case you want one word, the first word, that is the matrix heat exchangers, and you know that there are many types of heat exchangers, and out of that matrix heat exchangers on which I do my research, I will tell you what is all about, and maybe I will try to inculcate some interest in you so that you can also think of, yes, really if we can do something on this. Okay. Now before I go for that, let me see that a heat exchanger at cryogenic temperature, what are the characteristics it should have. The first of all, it should have high effectiveness. Now you know this in normal chemical engineering plants, their temperatures of the fluids is nearby room temperature, 300 Kelvin. Some streams are having temperature higher than 300 Kelvin, some streams are at just below the 300 Kelvin, so that you exchange the heat between them. But in cryogenic temperature, the cold fluid is, as I said, that it has to be below minus 150 degrees centigrade. So definitely heat transfer also in that region One stream will be extreme low temperature, other stream will be slightly better at high temperature, and you have to exchange the heat between those two fluids. Okay. Now the question is that if you have a, suppose if you have to liquefy air or nitrogen, you have a heat exchanger and then you have a jetty valve, and after jetty expansion some temperature is reduced and the returned gas is used in a heat exchanger to recover the cold before it comes out of the heat exchanger. I hope many of you know the Joule-Thomson expansion process, and by which we generate the low temperature. This is one of the process for producing liquid gases or liquefaction of gases, but there are many other processes. Now for particularly for this Joule-Thomson process, if you look into the simple calculation, thermodynamic calculations, it says that if the heat exchanger effectiveness is less than 85%, okay. Normally in chemical industries we talk of 60%, 70%, 75%, no problem. And but in cryogenic cases, if the heat exchanger effectiveness is less than 85%, then you get zero liquid output, no liquefaction. Okay. So that means what? It says that you need high effectiveness heat exchangers, or very top quality heat exchangers are required for cryogenic applications. Another reason behind it is that, or maybe this extension of this statement is that the main reason behind is that why a system fails if you go for very low, if you go for higher or lower effectiveness less than 85%, is reason is that the cost of refrigeration at low temperature is manifold than the cost of refrigeration at room temperature. As you go lower the temperature, even at liquid helium temperature, cost of refrigeration is the highest, and as you go in even 20 Kelvin or 77 Kelvin or 80 Kelvin. So lower the temperature, cost of refrigeration is the highest, and therefore any inefficiency in heat exchanger or ineffectiveness in heat exchanger will cost you to the cost of refrigeration, and thereby it comes that production of liquefaction or liquid. The liquid products will be reduced to zero if the effectiveness is reduced to a certain below effectiveness. In fact, in cryogenic exchangers, very high effective systems for producing cold, there we try to get effectiveness up to 98%, 99%. Imagine 99% effectiveness of heat exchangers. Yes, it is possible. Very compact heat exchangers are used for making this such a high effectiveness heat exchangers, and which we cannot imagine in case of normal chemical industries. So this term itself, it is a very complicated term. I need some time to explain it. The first one I have said that high effectiveness, and to have high effectiveness, those who are familiar with heat exchangers, they know that number of transfer unit, that is NTU, design NTU should be very high. Okay, because it goes by it goes by overall number of 1 by UA equal to 1 by H1A1 plus 1 by H2A2 plus of course this conduction resistance in the across the plates, across the material in between two fluids. Now this NTU, if you have NTU high, then there is a relation for say counterflow heat exchangers, that effectiveness is a function of NTU. So NTU should be very high to have this very high effectiveness heat exchangers, and to have high NTU, it is by definition it is U into A by m dot Cp, m dot Cp minimum. If you have minimum, whatever minimum m dot Cp, that has to be put at the bottom denominator, and in the numerator you should have U into A. That U is the heat transfer coefficient and area is the heat transfer area. That means you have to attack both on U and also on A to increase the NTU. Okay. So in compact heat exchangers, what I am going to talk today, that addresses to this high U and high heat transfer area both. Okay. Now the next part, in cryogenic heat exchangers, what is most important is that you should have low axial conduction, which is not bother. We do not bother at chemical industry heat exchangers that axial conduction whatsoever it is. What is axial conduction? Maybe to tell you in layman view, that is, you have a hot fluid. Say let us take about hot fluid. Say take helium. Helium in heat exchangers, where it has to be brought down to a temperature from 300 to 80 Kelvin. Okay. Now the heat exchangers, in the heat exchanger, helium is entering at a 300 Kelvin and coming out at 80 Kelvin. Okay. And by exchanging heat with a cold fluid. But let us take this particular stream, the hot stream, which is entering at 300 Kelvin and coming out at 80 Kelvin. Fine, but it has to pass through a solid medium. Some body of the heat exchangers will be there, over which, or the passages, fluid passages, holes or perforations, or maybe some flow paths through which this helium is flowing. What I mean to say, there is a body, solid material contact between this 300 Kelvin to 80 Kelvin. So this solid body of the heat exchanger, that will cause certain amount of heat short circuit. That means from 300 Kelvin helium, some heat will go to the body of the heat exchanger, and along the body that heat will be coming down to the colder side of the heat exchanger, and it will get back to the same stream. That is short circuiting. Okay. So that means what? The heat which is coming out of the helium at the room 300 Kelvin, and that came along the body, and finally it is coming into the same stream, that heat was not available to take part in exchanging with the cold stream. So that causes ineffectiveness in the heat exchanger, and it is very important for cryogenic heat exchangers, because the cryogenic heat exchangers are having very large temperature difference across the length of it. That means one end will be at high temperature and other end will be at low temperature. This temperature difference across a heat exchanger is so high in case of cryogenic heat exchangers. There you have this axial conduction problem very much. And the same is true for the colder side also. It is not only the warmer side, in the colder side also, colder side will have one side very low temperature and other side is the higher temperature. There also you will have heat leakage or heat short circuit because of this axial conduction. That means to have high effectiveness heat exchangers, 98% or 99%, you must have to have almost negligible axial conduction in axial direction, and there comes the greatness of the heat exchangers. Okay. So maybe as we proceed, we will further learn about how this axial conduction is minimized and how it is taken care in case of cryogenic heat exchangers. Then next part is that high compactness. Of course, you need high compactness. As a common man, you can immediately think of, yes, compactness is required, mainly because we need less space to put the heat exchanger, and but in cryogenic cases, it is not the less space we are worried about. We are worried about that it has to be smaller or compact, because the surface area around the heat exchanger is reduced. As a result, heat leak from the ambient is 300 Kelvin. Entire heat exchangers may be at the temperature of 20 K region or 80 K region or 100 K region kind of thing. That means if the room temperature is 300 Kelvin and 100 Kelvin heat exchanger, then definitely there will be good amount of heat transfer from the ambient to the heat exchanger. And all these heat exchangers, cryogenic heat exchangers, need to be insulated so that this heat load from the ambient is reduced or minimized. So that minimized will automatically reduced if you have a smaller size. Instead of big size heat exchangers where surface area is so large, if you can reduce it to smaller size, definitely amount of heat that can come into will come down. Okay. For the given same insulation where K is the same value for both the cases, because of the surface area is large, amount of heat that can come into this heat exchanger will highly come down. Okay, there is the point that you need compactness. But of course, the other one, that compactness will give you the space requirement point of view, that is essential in case of flight-borne systems. For example, if you have a satellite which carries this cooling system to produce the cold, to cool the infrared sensors. I hope you know infrared sensors, what are they? They basically take the images of any body at room temperature near about. Suppose the sensor is mounted in satellite, and satellite is picking up the waves that is coming out of the body at near room temperature on the surface. Suppose the sensor is taking photographs of a ground surface on the earth, maybe at night even, say taking the photos of the border region, whether any infiltration is going on or enemies are coming to attack or not. To take the photographs to take the images of that body, that human body, it will take the thermal image of those bodies which are at fairly room temperature. Now imagine, it will just take the thermal images. That means what frequencies and what wavelengths these are radiating. Every body, every temperature, because by virtue of its own temperature, it will emit certain amount of energy. Those energies, if it can pick up, if you have a sensor to pick up those energies, you can figure out that yes, there is a body having this temperature and that is moving around. You can figure out just images. You cannot figure out whether male or female, but you can figure out very well that some animal or something is moving, some object. If there are a large amount of crowd is at the near the border, you can figure out yes, there are human beings getting accumulated near the border. Now sensor is meant for to record the energies or the waves whatever is coming out from these room temperature bodies, which are or room temperature may be slightly higher, which are placed at the border or on the ground, whose photographs we are taking. Now imagine if the sensor itself is at the same temperature, that also will generate the energies, waves, and that will cause the noise. So that means what? You have to minimize that noise that is generated by this same sensor itself. So to do that, that sensor has to be cooled to a very absolute zero temperature, near absolute zero temperature, near absolute zero, not a very zero. That is not possible. Absolute zero is not possible, but still as low as possible we try to cool it down. Okay, maybe 10K, 4K, whatsoever we do it, so that the noise created by the sensor itself can be made to negligible. So that whatever it picks up that comes from the ground or from the if it is a military purpose, from a distance, not from the chamber where it is located. So that to cool that sensors, you need to have a very small cryogenic systems which will generate such a low temperature. Maybe very small amount of loading is required. Power requirement may be very small, milliwatt power requirement, but you need to have that environment where this low temperature is generated, and then sensor is placed there and the sensor will be cooled. Okay. So that means what? There in those cases, that is flight borne system in satellites, you need the space requirement should be also minimum. Therefore, if you have a heat exchanger which needs very less amount of space, that is very much useful for satellites. Okay. I hope you don't mind if I cross more than 1 hour. Okay. Okay. So then less external heat leak that we have talked. Then materials should remain ductile at cryogenic temperature. Now heat exchanger, while making heat exchangers there are many materials, but for choosing the materials or while choosing the materials for cryogenic applications, you should be very careful that they don't become brittle at low temperature. Materials like non-metallic materials like polymer, plastics, and this, and then some basically non-metallic materials, they become brittle. Even other metallic materials also become brittle, but there are materials like stainless steel, copper, aluminum, they can work up to liquid cryogenic temperature, even up to down to 4 Kelvin. Though there is a reduction in brittleness, there is a reduction in ductility, but still they can hold the required pressure or strength, and you can work with it. Okay. So this is material selection becomes important because of its low temperature, where there is a transition from ductile to brittleness. Okay. Then last part, that design should take into account the fluid and material property variation. As you go down to very low temperature, and if the heat exchanger is to be designed for a wide range of variation of temperature, starting from 300 to 80 Kelvin, or maybe 80 Kelvin to 20 Kelvin, or maybe 20 Kelvin to 4 Kelvin, such a wide temperature variations, the properties of the fluid and temperatures, they all vary with temperature. Okay, they all vary with temperature. So therefore, one must, while designing the heat exchanger, one must take care of these property variations, both thermal property and the mechanical property variation with temperature. One should take into consider them while designing the heat exchangers. So these are the critical issues while designing the heat exchangers in cryogenic temperatures. So then next I will go to the different types of heat exchangers that are used. You can see there are a list of heat exchangers. I have listed them, and they have been arranged as per their size. How big are they? The bigger of the heat exchangers type, they are at the very first level. Then slowly I will come. They have been arranged with smaller and compact sizes. That means what I mean to say, the last one will be the most compact heat exchanger, and the topmost one will be the bigger one, very bigger one. And not only that, shell and tube, coil tube, and both those two, shell and tube and coil tube, those are used in a very large tonnage capacity plants, very large plants. and these are very big heat exchangers. But as you slowly go to the down, that is aluminum brazed plate pin, then concentric tube, Collins tube, they are for smaller plants they can use. And this third one, that is aluminum brazed plate pin heat exchanger, they can be used in bigger plants also, large plants also they can be used, because they have the advantage that they are very compact and per se with similar performance as the other two heat exchangers, but they need small space and their performance also much better than the other heat exchangers. So slowly in these bigger industries, bigger plants, this third one, that is aluminum brazed plate pin heat exchangers, they take care of, they replace the other type of heat exchangers which are otherwise being used very commonly in industries. Okay. And in fact, in earlier days when this aluminum brazed plate pin heat exchangers were not coming up very satisfactorily, that time in those days shell and tube and coil tubes were used, and these are also being used, but more often people go for aluminum brazed plate heat exchangers because it has compactness, very high compactness or better compactness, better performance compared to the other two heat exchangers. Okay. Now I will try to tell you that how these heat exchangers look like, and finally I will come to the last but one, that is matrix type, and I will talk more about that matrix type heat exchangers on which I am working, and details I will tell. Okay. And whatever I talk about this heat exchanger, the experience or the kind of discussion I do it in this in this lecture also will be useful for your any other type of heat exchangers also. So now I will go to the different types of heat exchangers, and then I will slowly introduce the what is matrix type heat exchangers, and then also I will touch upon all the types of heat exchangers so that you have some understanding about their different scales, different types of applications and what it is meant for. Now let's see, this is very simple. You might have seen in many places that is shell and tube heat exchangers, and it has pointer is there, pointer. It has large number of tubes, as you can see in this side there are a large number of tubes, and they are placed in an enclosure, and inside the enclosure in between the enclosure and the pipes or tubes you have the other fluid. That means this type of heat exchangers are suitable, that is when you have a large flow rate of one fluid and the other fluid is having rather less amount of flow rate. That means less amount of flow rate and high pressure, those fluids will be passed through these tubes, and the other fluid which is at rather low pressure but large flow rate, that can be passed to the shell side. Shell side means this color one which is entering here. Okay. So this is as you can see here, see one fluid is entering here, or this is entering, or maybe outlet also, it does not matter, other fluid will be passing through these tubes. Now as it comes here, it will find some kind of guide vanes or guide supports. Half of it is covered, not fully, so that it will be guided, the fluid will be guided to move in this direction, then it will go from the bottom of this vane, guide vane, then it will go up, then again it will get circulated through this, and finally it will go up, then again it will be circulated like this, and again it will come down like this, it will go like that, like a passage will be formed. Now you see there is another baffle here, this is another baffle. So this baffle will make the fluid to go from this direction to this direction, because baffle will stop it. Then again on top of the baffle it will come in this direction, and there is another baffle, this it will go from the bottom baffle, and like that this flow is made to move circle or move around and around and around with a good turbulence. As you know that turbulence will help in heat transfer. So therefore with good turbulence this other liquid will come out in the other direction, and while this tube will get heat transfer with the exchange heat with this other fluid. Okay. So this is shell and tube heat exchanger. Its compactness is compact, it is not compact at all, and but it is used in ground installations, large plants where large amount of fluid has to be handled. Now you see this is another heat exchanger called coil tube heat exchanger. Now there are many number of tubes, large number of tubes. Here also through the tubes you can pass a large amount of fluids also you can pass, and the construction wise you have fluid tubes for carrying one or more type of fluids through these tubes, but entire tube bunch will be placed inside a outer casing. Now the space between these tubes and the outer casing and inside the tubes, there are lots of empty spaces. Through those empty spaces you put or you pass another fluid with which heat transfer has to be taken place. So heat transfer will be between that fluid which is passing through the empty spaces of the fluid and the tube. So therefore it is a coil tube, and you can imagine the size of this heat exchanger. It is more than a human height, and it is large, very large. So it is a big, larger plants, larger installation cases it is used, larger applications it is used. Now see, the same heat exchanger can have different types of possibilities of different types of fluids. You can have 3-4 types of fluids, you can have multi fluids, you can use it, and this entire heat exchanger will be placed inside the casing, and the fluid will be passing through this in between fluids tubes. Whatever space is available through this space, your fluid will be passing through. Okay, so this once again you can imagine that how big these heat exchangers are. Okay, now this is aluminum plate fin heat exchangers. This is you just take a plate, and this plate is deformed, or maybe in this shape it is made so that this point is in contact with this plate and this point is in contact with this plate. Therefore any heat, any fluid is under this plate will have the temperature of this fluid temperature, and with this plate, because this point is in contact, heat transfer will take place by conduction, and that will travel along this fin. These are called fin, along this fin, and by conduction heat will come there, and once again this point is in contact with this plate, and over this plate you have another fluid, so that the heat finally will go by conduction from this point to this point, from this point to this point, and this point to the fluid top. That means though it is shown separately, but they are placed together and welded. This point is, and this point, these points are welded along with the plates, and finally this side and that side, that is blocked. So therefore you can have one fluid in this direction, and over that you can put another similar one for another fluid. So like that heat transfer between these two fluids will take place, and those two fluids are separated by these plates. So that is why it is known as plate fin heat exchanger. Now you can arrange this one in other directions also, so that it will become a cross flow type, and you can have multi fluid, multi stream heat exchanger possible, and this is what is shown here in a combined unit. This is really very efficient so far as large application point of view, large size heat exchangers point of view, and they are compact, they have high effectiveness, low pressure drop, what all is required for a large size plants, and they are replacing slowly all types of cell and tube and your coil tube heat exchangers. Okay, they are replacing all, because now the manufacturing technology has come up so nicely and it is so matured now. We are easily able to manufacture these heat exchangers, and they occupy less space, so that is the major advantage, and performance is still higher than the other heat exchangers. Okay, now then I am coming to the medium size to smaller size plants. These are all tube in tube heat exchangers, and this is there are various types of designs. One is this inner tube, and this is outer tube, and one fluid will be flowing through the inner tube, and you have a solid oval here. Across the solid oval, heat will be transferred from this fluid to this fluid, and this is a standard practice in heat exchanger, tube in tube heat exchanger. Now you can also have multi tubes placed inside another tube. So you can accommodate 4 types of fluids: 1 fluid, 2 fluid, 3 fluid, and another fluid is in between the tubes, the inner tubes and the outer tube. Okay. Similarly, you can have similar same thing as tube in tube, but there is a difference. You can put some wires here in helical form, so that the fluid, whatever is flowing through this annular space, that means in this space, that is guided by these wires, so that they make round and round and then go out. That means that way heat transfer can be enhanced because of this motion. This is by guiding this, by using this wire turbulator, by guiding that, this turbulence will be created over the fluid, and therefore Reynolds number will increase. Therefore heat transfer coefficient in the shell side or annular side will be increased. Okay, so this is improved version over this. Then you can also have heat transfer between several fluids having soldered. This tube is soldered with this is soldered with this is soldered. So heat transfer between tube to tube will be much higher because of the solid contact between this fluid and this fluid. Not only solid contact, you have a good amount of joining between this tube and this tube. Okay. So therefore heat transfer mechanism, heat transfer is increased. But however, these are for smaller systems, and relatively less efficient heat exchangers can be made out of this configuration. Not very efficient effectiveness, and not very compact either. Okay. But as you go to the next one, this is also a heat exchanger. Is a tube in tube. Basically, it is also tube in tube. You have large number of tubes, say tube 1, tube 2, tube 3 and tube 4. But in between the tubes, instead of soldering them, you can put this type of helical ribs, so that these ribs will be in contact with this tube and this tube, and in between the ribs you can pass on the fluids. Therefore, heat transfer from this fluid to this fluid will be transferred across this wall, as well as these ribs or helical ribs will act as fins, so that faster heat transfer will be there from this fluid to the wall, then from the wall to the this side, this fluid. So like that this has somewhat improved heat exchanger, and Collins used it for its liquefier. Now you see, this is the one which I am going to talk about, and this is one of the designs. There are many types of matrix heat exchangers. One of the design I will show here, that is, you have a stack. This is a stack of different plates. You know, this one plate you see, this is one perforated plate which is having very small perforations, very tiny holes. Here also holes, and one set of holes will carry one fluid, another set of holes will carry another fluid, and this is purely a copper plate, and in that plate you are selectively putting holes here. Now what happens, you have a stainless steel spacer, we call it a spacer, and this is hollow space, this is hollow space. I take the spacer and put it on top of it. Therefore what happens, that you are creating a couple of things. For example, you see that perforated plate, then spacer, again you have a spacer and plate, you stack them together. After that you do it, you go for bonding. How do you bond them? You put it in a high temperature and high pressure. High temperature means temperature of around 850 degrees centigrade, or if not little bit more, maybe 900 degrees centigrade also you can go, and you have to apply pressure after that, in that, so that this copper will reach to its softening temperature, that is, it will become somewhat soft, and thereby some molecules of the copper will diffuse into the stainless steel, and the vice versa also will take place. Some stainless steel also will diffuse into the copper, and thereby on the process there will be diffusion bonding between the copper plates and the stainless steel plates, and therefore it makes a very complete unit. So therefore if you put them together one by one, and if you bond them by diffusion bonding, you are able to generate a thorough passage for this fluid. So because these red colors are in this side, red colors, this color, red color, and they will make a thorough passage for one fluid. And similarly, these holes, this set of holes for consecutive plates, these holes, they will be directly connected, and that will make for passage for another fluid. Heat transfer will take place from this fluid, these holes to these holes, fluid from these holes, heat will go from in this direction, and finally this will cross the wall in between, and finally it will go to the other set of holes, and through this other set of holes, by convection heat will go to the other fluid. Therefore heat transfer will be in this direction, in across this direction, and this is a copper plate. Now what happens then, what is the role of this spacer? The role of this spacer is that as you use, this is, as I said, this is a copper plate. Copper is a highly conducting material. Thermal conductivity is about, at room temperature, is around 414 watts per meter Kelvin, and if you put only copper plates, no stainless steel spacer, then what will happen, that entire body is made of copper. Now axial conduction will be very high. because copper has a very high conductivity. To minimize the axial conduction, in between you should put a stainless steel whose conductivity is somewhat 10, 12, 14 watts per meter Kelvin compared to 400 watts per meter Kelvin for copper. So with comparing with the conductivity of copper, stainless steel become an insulator. So because of that, by virtue of using this one spacer, we are minimizing the axial conduction effect. Okay, and by using this spacer, another thing we are doing that, you know, this as the fluid comes out from here, it will find an empty space here because it is empty, hollow. So in this empty space, it will get a chance to mix thoroughly. Therefore, flow maldistribution in between these holes will not be there. That means even if in one case there is a flow maldistribution, next time whenever it gets this spacer, it will get thoroughly. Now you see another type of heat exchanger, though it is not normally used, but it can be used for cryogenic applications also. You have different plates. Those plates are having small channels. You can cut these channels by using a photolithographic technique, and then you can arrange these holes in such a way that in this place your holes are in this direction, and another in the top of this plate you can have another holes in this direction. Therefore, they can make cross flow. One fluid is going in this direction to this direction, another fluid from this direction to this direction. So that's a cross flow heat exchanger, very compact, and you can stack them together, and you can diffusion bond them or diffusion weld them. That is also, this is basically known as printed circuit type heat exchanger, PCB type. Okay, printed circuit cross flow heat exchanger. These are also very compact, very high compactness or surface area density. You know, most commonly used term is surface area density, that is area of the surface area divided by volume of the heat exchanger, and it is also related to the porosity. Porosity is defined as that total volume of the heat exchanger divided by the volume of the material on which we are making the perforations. Okay, so this is another parameter with which we can define the heat exchanger. So these are the various terms. Hydraulic diameter, you know, the smaller the diameter, you will have the higher hydraulic resistance, hydraulic diameter. Okay, then here this chart tells you that what type of heat exchanger is where does it lie. This is from a standard book, I have copied it. This is Hazel Grips. You can see different type of heat exchangers. Let us take shell and tube. Shell and tube and tube and tube heat exchanger, they are in this region. That means, you know, this line tells you if your heat exchanger is having compactness in this region, that is a compact heat exchanger, that comes under the category of compact heat exchanger, and if your heat exchanger is in this region, that does not come. So this is the heat transfer surface area density. This line basically it comes around 700 meter square per meter cube. Sorry, this is not meter M3, it is a meter cube. So if the 700 meter square per meter cube, if your heat exchanger crosses this type of heat transfer area density, then we say that it's a compact heat exchanger. By definition, it is by definition that if your heat exchanger is having greater than 700 meter square per meter cube, then you say that's a compact heat exchanger. If it is less than that, you say that is non-compact. So heat exchangers like tube and tube, shell tube, and plate heat exchanger, this I have not discussed what is plate type of heat exchanger. This is basically used in your agricultural industry, food processing. So that I will not talk. But you see the other heat exchanger, cryogenic heat exchangers, normally we talk of in this region, that is slightly, it starts from somewhere 750 or so. Then in this region, cryogenic heat exchangers, that is compact shell and tube heat exchangers, or you can have fin type heat exchangers, lowered fin type heat exchangers, and matrix heat exchangers are in this region. That means quite somewhere here, it starts from around say 800, 900. So not 900, so 1900 to as high as 6000 meters square per meter cube compactness you can have. But you see the most compact heat exchangers you can see here, printed circuit heat exchangers, whatever I have shown you, PCH, last heat exchanger, and micro machined. These are having very high compactness, very high effectiveness, very high compactness, but you can have it in a very smaller applications, not a bigger applications, because of large pressure drop associated with in micro channels. Okay, So this is what is the, it is interesting to note that human lungs is the most compact heat exchangers available in nature. Okay, so you can see somewhere it is how many, say 10 to the power 4, then 10 to the power 5, not 10 to the power, that is 2 into 10 to the power 4. So much of heat transfer area available in human lungs. Human lungs, it controls also body temperature, and as the blood brings hot blood comes to the lungs, and it takes the cold air from outside, and therefore heat transfer takes place. So therefore this lungs, having so many limbs in the lungs, it has a very high surface area, and it is the most compact heat exchanger available in the nature. And compactness, you can see here the number of holes, these are the tube diameter. As you see, the tube diameter is increased and reduces, and the number of tube is increased, therefore it is a compact, means it is a very tiny tube diameter, and the more manifold increased in tube numbers. So therefore we call is the compactness, means it is a matter of degree. So this is how it is explained. Okay. Then matrix heat exchanger, that is the main theme of this today's talk. This is so far whatever I have talked, that to tell you that where does this matrix heat exchanger lie. Okay, so here I will tell that what all works I have done, and the practical aspects of various issues like designing, then manufacturing, then testing, all this I will talk. Okay, this is the second part of my talk. Okay, so before I go for that, we have to talk on configuration, different types of configurations of matrix heat exchangers we have, then some design issues we will talk, then selection of material, then fabrication, then testing. Now configuration wise, this configuration you have already seen that you should have a plate spacer combination. But what is different, what I want to say in this slide is that not only the this rectangular shape plates, you can have any type of shape of the plates. It can be circular, it can be spiral channels with circulars, those things I will come little bit. But you see, as I said also, they have to be diffusion bonded. Now you see the advantages of this type of heat exchangers. Maybe some of the points already have covered. You see it has very high compactness, as high as 6000 meters square per meter cube. It can be designed for high effectiveness, 98% or more, easily one can design. It has low pressure drop because of large number of holes, and can be used from near absolute zero to about 800 degrees centigrade. This is the major advantage of this type of heat exchanger, because you are making it by diffusion bonding, and you have a metal to metal bonding by diffusion of one metal to the other. So therefore till you reach to the bonding temperature, that means 850 degrees centigrade or 900 degrees centigrade, it can be used as a heat exchanger. That means if you have a fluid of this temperature, you can still use this heat exchanger. So there is a wide temperature range that is up to which you can use, from near absolute zero. If it goes to even 0.001 Kelvin, this heat exchanger will still work, because it does not structure point of view, it does not fail. And also if it goes to very high temperature, it does not fail. Negligible flow maldistribution, as this I have already described. Then can be designed with multi-channels for multi-fluid heat exchanger, multi-fluid heat transfer. That is also possible. You can design it for many channels inside. Some of the channels I will show you. Now see, this is a simple, this one I have shown you, that is channel 1, channel 2. And you can design like this, channel 1, channel 2, and again same channel, that is same fluid is divided into two sides, so that it transfer from here to here as well as from here to here, you can have it. So that way you can have better heat transfer, or you can have more mixing with the channels, that is fluids. That is, this is one fluid is like this, and then another fluid you can have this type. So this is called finger type, this is called 3 channel, this is 2 channels. Similarly there are other designs also. Sorry, so it is in circular design. Say you can have one fluid channel here, another fluid channel here. This is circular annular type, and circular finger type, you have one fluid here, channel 1, another fluid in this direction, in this form. Or you can have a spiral wound. That means one fluid is, this yellow color is one fluid, and that is wound by another fluid, that is channel 2. You can understand how they can take it transfer. Heat transfer will be across this wall only. Okay, from one fluid to the other fluid across this wall, this direction as well as in this direction. Okay, so there are still other variations. You can see them. that these are multi-channel heat exchangers, 1 channel, 2 channel, 3 channels. For example, if you have a very high pressure fluid, you can make this type of channels, one fluid high pressure, low pressure, again high pressure, again high pressure, low pressure, like that. You can arrange them such a way that if it is a very high pressure, you need to design only for this square, this much of space you have to design, so that this wall thickness can be reduced. So that is why this advantage you have, this multi-channel you have the advantage. Or you can have different type of circular channels also. In each channel you will have multi perforations, and also you can have different another design like that. This is also in circular design, and also this you have a square wire screen. It need not be plate, you can have also wire screen, and over the wire screen you can put a design in such a way, this spacer is designed in such a way that by bonding they can easily create different fluid channels, one channel, then second channel, again high pressure channel, this is low pressure channel, this is high pressure channel, like that it goes on. So various designs are possible. If you are interested, you can look into the literature, you will get them. This is another interesting design is that you have this plain perforated plates, and over which you can have a tube, and through the tube you are sending liquid helium, and that liquid helium is a colder liquid, and that will be used to reduce the temperature of the gaseous helium. This is in a helium-2 refrigerator, and because in the liquid side you have a large heat transfer coefficient, you need less amount of surface area here. So therefore you have just only one tube which is soldered over the entire heat exchanger perforated plate stack will do the job. So this is one of the another design. So there are various possibilities of designs. Now this is another aspects of the matrix heat exchanger, that is you can have the perforations in line. That means one perforation in one plate is matching with the other perforation of the other plate, like that is inline holes, and if they do not match, if they are offset, if the holes are offset, we call it shifted holes or offset holes. Okay. Now design issues, basic design issues, I will not take your much time, but all I wanted to say that conventional approach you have that 1 by UA is nothing but resistance due to convection in one fluid, then conduction resistance in the tube wall, and or the in between wall material material conduction resistance, and the convection resistance in the other side fluid 2. And but in this case, because you have a material over which the heat has to go from the fluid to the plate, and from the across in the plate in the lateral direction heat has to go, and after that when it comes to the next set of holes, again by convection from the holes it will go to the other fluid. So what is difference between this and this, that you have a good amount of thermal resistance while heat is flowing through the plate in the lateral direction. So that resistance you have to take into account by incorporating the effectiveness of the plates. Okay. So but still this is a primitive approach, but in actual practice one should consider the convection heat transfer between this fluid to the plate, then conduction through the plate, and again from this plate by convection to the fluid. So that differential equations are to be solved simultaneously. Those are written here, and just by solving these differential equations one can reach to the desired performance, or can design the heat exchangers. Now selection of materials, there are various materials is possible. For low pressure applications one can go for aluminum as the plate material, and non-metallic materials like neoprene, nylon, paper, plastic gaskets, polyester, FRP as special material. But it is for low pressure applications, they can be bonded by adhesive joints, and those are not normally used. But most of the cases we use this copper and stainless steel, because copper is high conducting and stainless is much lower, one order of magnitude almost less than the copper. So they can be used for high pressure applications and wide temperature range, and they are made by diffusion bonding, as you know. Aluminum and titanium, they can be used for space applications, because weight of the aluminum is about 50% of the weight of the copper, and similarly weight of the titanium is about 50% of the stainless steel. Therefore overall heat exchanger, for the same heat exchanger duty, if it is a space applications, we can reduce by the total weight of the heat exchanger by about 50%. So therefore aluminum and titanium are the preferred material for flight applications. But the problem is that bonding between aluminum and titanium, lot of works need to be done to ensure that good bonding between aluminum and titanium, because aluminum does not bond properly with anything. Aluminum is very difficult to bond. Okay, then silicon and glass for medical applications. Silicon is also very highly conductive if it is properly made, and then with reference to silicon, glass is a special material, and you can build them together, and it can be very tiny material, it can be made so that they can be used for cryosurgical probe integrated with jet cooler, that is mixed or the miniaturized jet cooler, what I said. In that you can use this type of materials for heat exchangers. Okay. Now, as I said that copper and stainless steel are the best material for this perforated plate heat exchangers. And why are they so very why they are preferable? Some of the reasons are written here. They are highly compatible for diffusion bonding, can be designed for high pressure applications, wide temperature range, this you have known already. Then thermal conductivity, this is important. Thermal conductivity of copper increases with lowering the temperature. Plate conductivity, if it increases, then you are better off. At low temperature, as you go down to lower temperature, if the plate conductivity increases, yes, that's a benefit for us. And at the same time, the stainless steel conductivity decreases with lowering of temperature. That means as you go down to lower temperature, the heat exchanger becomes more appropriate for as a heat exchanger. Okay, because they are just exactly working with what is required. Then thermal expansion coefficient of copper and stainless steel, they are very close, and so that they can operate at even very high temperature or too low temperature, so that their thermal expansion coefficient can be, they will not cause much stresses so that the heat exchanger will fail. It does not happen because their expansion coefficient are very close. Okay. Now, bonding method, there are different bonding methods from fabrication point of view. As I said, the diffusion bonding is the most preferable method, but however one can go for adhesive joint, which does not have much strength and it has gas contamination, because adhesive joints will degas lots of gases. Then soldering and vacuum joint, vacuum bridging, yes, strength of the vacuum joint, the soldering joint depends on this the solder, so not much of high strength it cannot take. But another problem is that the solder material and the bridging material can block lot of holes, so that disadvantage is there. Finally, this does not have any filling material, it is only diffusion from one metal to the other, so it is a best method for this type of heat exchanger. Then I will go to the fabrication. Fabrication means diffusion bonding is a process. This process I am using it. The diffusion bonding is a process of bonding two similar or dissimilar metals by interdiffusion of atoms from one to the other under high temperature and compressive load. Okay, this I have already discussed. Then conditions are that you should have temperature, you have to find out what temperature you should use, then what load you have to use, then duration of bonding. These three parameters are the main parameter, and usually during diffusion of bonding we use this type of profile, that is heating profile. Say for example, this diagram, it says that heating from it takes after it's a temperature you see about 850 degrees centigrade. So we are slowly heating after maybe it takes about 2 hours to reach to 850 degrees centigrade. Then after that at 850 degrees centigrade we keep it for about 1 hour, and after 1 hour we switch off the heater. Then we allow the this system to cool down by itself, and you will have high vacuum during the operation, so that automatically its temperature will come down, but it will come down very slowly because you have the vacuum inside. Now the loading point of view, when you apply the load, because you have to apply the load, then only diffusion will take place. So initially we do not apply any load, but the moment it reaches to this 850 degrees centigrade, we apply the load to a pressure of about 10 MPa pressure. Then that 10 MPa will continue till the temperature of the body or heat exchanger reduces to almost room temperature, 30 degree. So till then your pressure should be there. After that you can release the pressure and you can take out the sample or heat exchanger. Okay, these are the some samples we have made. This is copper plate, and these are the spacers. Then these are the headers, and you can see that they do not look like a copper plate, because the copper plates have been coated with nickel. If you have a nickel interlayer, very thin nickel interlayer, say about 20 to 30 micron, coppers have been coated with nickel by using electrolysis process. If you have a very thin nickel interlayer between copper and stainless steel, this nickel will help migration of the stainless steel to the copper and the copper to the stainless steel. It will just it helps like a catalyst. So therefore, to get better diffusion bonding, you must have nickel coating, and this photograph is taken after nickel coating over the stainless steel this one plates, copper plates. The copper plates, you can see the perforations here, and they have been perforated by chemical etching or photolithography. Same thing, photolithography technique by chemical etching, they have been perforated, and the diameters of the hole is about 0.6 mm, and the plate thickness is 0.4 mm, and this spacer thickness is 0.5 mm. Okay. Then cleaning is a very difficult task. I mean, unless you do proper cleaning, you are not going to get a leak proof heat exchanger. This is one of the major challenging issues. Though it appears to be to you, maybe okay, oh, cleaning ho jayega. It is not that. Cleaning is the most important part to get a good diffusion bonded heat exchangers. If you are not taking proper care while cleaning, then you will not get good heat exchanger with a leak proof heat exchanger. You will get heat exchanger with bonded very everything, but the moment you go for leak testing, you will see that it is leaks are appearing. It is only the cleanliness which will ensure the leak proof joint. Then for that, you have to ensure that everywhere enter the all plates, all spacers, in every spaces of the spacers they do not have any dirt particle. Okay, it's a rigorous procedure and it's a very strenuous also. Every plate, every spacers, you have to observe it properly, and you have to see that no particle, no stains, no black spots, nothing is there. It's absolutely, it has to be clean. Then only you will get it. Initially, I have also lost many number of heat exchangers because of this cleanliness problem. But later on, I understood that how it has to be cleaned, and finally we got the heat exchanger. Okay, so these are the procedures how to clean the plates and spacers, and this same procedure you can use it for other applications also. Here stainless steel material has to be cleaned or copper plate has to be cleaned. You can use the same procedure. It will be used for other applications also. Okay. Now after stacking the plates and spacers, this looks like that how they look like in a stack. You have these plates and spacers are stacked, and they are guided by these rods. These are tungsten rods. These are, we call it as post. They are basically rod, some small 2 mm rod, and these tungsten rods can go up to very high temperature. They do not become soft, and because of they have been put here, and then this is used as a guiding of these plates and spacers. And this is the header. This is another header. These are the 2 rams, top ram, bottom ram, and after that these top ram can slide over these rods or these posts. So an entire thing I put it into the this one diffusion bonding machine and press them. We have a diffusion bonding machine in our system, in our center, and so this is the machine we have it. It is about 5 ton capacity, and this is the vacuum chamber. Inside the vacuum chamber we put the entire stack, and this hydraulic jack is there, and that is this ram comes down and presses it, and while heater is there inside, that heater is heated by supplying the power supply which is behind of this control panel. Okay. Now you can see that that heater stack, whatever I have made, that stack is placed here. After that we will close the door. That door will be closed. Then it will be pumped for vacuum, and after vacuum is reached, we will switch on the heaters for this. Supply the power supply to these heaters, and you will heat it up to the temperature of 150, and after 1 hour, and it is a whole day affair to get one heat exchanger. One whole day it has to be lost to get entire process. So these are some of the fabricated heat exchangers. This is 50 plates, this is 75 plates. I have gone up to 100 plates also. There are heat exchangers, I have 100 plates, but because of the limitation of the machine we have, we are not able to generate more than 100 plates, because the total length of the heat exchanger can be about something 17 centimeter, not more than that. Out of that you have 2 headers, so it takes more than 100 plates is not possible to accommodate. Okay. Then after making the heat exchanger, you have to accept it for your leak testing and leak rate measurement. Major leaks we find it out by pressurizing it to a high pressure, say about 15 bar or so. Then we dip it into water, and if you have a major leak, immediately bubbles will come out, and looking at that you can say that okay, no, it cannot be done. But after raising to a pressure of say something like 15 bar or workable pressure, whatever you are looking for, If you see that there is no bubble coming up, that means you can be sure that at least at this stage there is no leak. Then what you do, take the heat exchanger, dip it into liquid nitrogen, keep it for some time, then bring it to the room temperature. Again dip it into liquid nitrogen, keep some time, bring it to the room temperature. This is called thermal loading. After several thermal loading, maybe something like 10 to 15 times, then you again do the same testing under the water and see if any bubbles are coming up. Okay, because putting into low temperature cryogenic temperature and bringing it to room temperature will cause thermal stresses to the heat exchanger. If there is really any weak point in the joining, that weak point will fail because of this thermal stress, and again leaks will appear. So after doing that, if you are seeing that there is no bubble still after doing 15 times, then you can think of that, okay, this heat exchanger is acceptable. But even then you have to go for leak testing by using mass leak detector spectrometer or mass spectrometer leak detector, MSLD we call it. So in that you can find out what is the leak rate. Okay, so there is a special technique, there machine is available, and typically your leak rate should be something like 10 to the power minus 7 torr liter per second. Okay, so so this is how you have to go for your acceptance testings. Okay, now testing of the heat exchanger. This I will not elaborate because there are various methods available for testing the heat exchangers. The one we have used is this one, very simple, that is by using liquid nitrogen. This is a vacuum chamber. Inside the vacuum chamber I put my test heat exchanger here. So from cylinder helium is coming, and there is a compressor here. From the compressor at a pressure of say 9 to 10 bar, I take this helium in this direction. Then this is a hot helium. It is the test heat exchanger. In the test heat exchanger, it will receive cold from this return stream, and after that its temperature will come down to say near around 100 Kelvin or so. And then this heat exchanger, this helium is taken to liquid nitrogen bath, where liquid nitrogen is put inside, and using the liquid nitrogen this helium gas temperature is brought down, and then that cold helium is about 80 K will be put inside as a cold stream inlet temperature, cold inlet stream, and then by exchanging heat in between these two, we will find out the performance of this heat exchanger between the room temperature and the 300 Kelvin, 80 Kelvin, how does it perform. So with this simple arrangement, there is a data acquisition system, online data acquisition system, everything is simple. But here I will tell you that by measuring these 4 temperatures, you should take extreme care of measuring these 4 temperatures rather than relying upon the measurement of this liquid nitrogen boil off because of this heat load here, which will give you the ineffectiveness of heat exchanger. But I would suggest you measure these 4 heat exchanger heat temperatures very accurately, and based on that you can calculate your effectiveness of the heat exchanger. Okay, and then these are different components, these are written there. So now this is the experimental test setup. You have the heat exchanger here, and this is liquid nitrogen bath, and this is flow meter, regulator, then it is a warm up coil before the gas goes back to the compressor. Okay, now this is the test setup. We have an online data acquisition system, then testing is being done, and this is liquid nitrogen is going through this tube and getting into the liquid nitrogen tank, and data are being recorded. Only 4 temperatures are recorded, and flow rate is being recorded by this controller, mass controller, flow controller, mass flow controller. Now this is very tricky thing, that is we have options that we can put sensors inside the fluid stream, or we can put the sensor on the top of the tube. Many cases we are inclined to put the sensor on top of the tube, so that that is very easy to mount. Mounting of the sensor is very important. So you will think that I will put the sensor on top of it and tie it. That will not give you accurate result of the fluids. To get accurate result of the fluid, you should put the sensor inside the fluids. Okay, so you should put this is the sensor, and this sensor is to be placed inside, and fluid will be passing through this through this, so that this after putting this one, this will be sealing the gases. Gas will not come out through this, because vacuum is here. You have the vacuum outside. So this nut is tightened across these threads, and this sensor is there, and there is a hole inside this nozzle, and all wires are going through these holes, and they are connected with a capillary tube. all 4 wires, you have a 4 wire mechanism to measure the temperature resistance of a platinum sensor. This is a platinum sensor basically. So these 4 wires will be taken through this capillary tube, very thin capillary tube, so that the heat inlet through the capillary tube is minimized. Then finally at the outside of this vacuum chamber, you can put them together and they can seal them by using arrow light. Here it is fairly room temperature, so no problem, we can put arrow light here, but at these places, all these places you have to do it by brazing. Okay. So this is a specific techniques. Since you are having this slide, you can use it, that how to mount a sensor inside the fluid, and this is a very tricky aspect, nobody will tell you, but if you can get it, it will be useful for you. Okay. Then this is how you can connect the wiring for your data acquisition, online data acquisition. It is a 4 wire measurement by using PT100 sensor. How do you do it? And it needs a constant current source and then the voltage recording. And if any one of you are interested further details of it, you please contact me, I will tell you the details. Okay. Now this is the after measurement in the experimental setup, what we found that this effectiveness of the heat exchanger, as you reduce the mass flow rate, initially there may be some improvement in the effectiveness, but finally after some time it reduces. You know why? And there are, you can see there are 2 lines, one is green line and the red line. And you can see this A is measured hot effectiveness and measured cold effectiveness. What is hot effectiveness? What is cold effectiveness? Is that, you know, heat exchanger effectiveness in balanced flow condition is what? TH in minus TH out divided by TH in minus TC in balanced flow. So this is hot effectiveness. Cold effectiveness will be TC out minus TC in divided by TH in minus TC in. This is cold effectiveness in balanced flow. So there is a difference. That means if your measurements are not pakka, if there is a error in measurement of temperatures, then these 2 terms, though they are supposed to be the same, they are in theory they should be same, because your from energy balance point of view, m dot Cp into Th in minus Th out should be exactly same as m dot Cp into cold fluid m dot Cp into Tc out minus Tc in. They will not match if your measurement is not proper. If there are some errors in the measurement, then it will be different. Because of that, you see the small minor differences here between these 2 measurements, this hot effectiveness and cold effectiveness. So but however, you can see that because of our accuracies in temperature measurement, we see the very little difference in effectiveness. So that is what is a very important aspect of it. Okay. Then this is pressure drop measurement. Pressure drop measurement is another issue. Every heat exchanger should be tested for its pressure drop and also its thermal performance. Pressure drop is something hydraulic performance, and if you have higher pressure drop, then that heat exchanger is of no use, because you have to pay in the compressor to raise the pressure and then send the fluid or pass the fluid through the passages. So this pressure drop measurement, we have done it separately in outside. That means this is the heat exchanger. We put this thing. There is a pressure. You know, this is U tube. There is a U tube. Inside the U tube, we put demineralized water, DM water we say, and this is a plastic capillary tube. It is at room temperature we are measuring, and then high pressure gas air is coming through this regulator, and we try to measure the pressure difference across this heat exchanger, and this is the recorder for that. Now this data says that different flow rate, how this pressure drop takes place, we have measured it, and at different number of plates and flow rate it is there. So then there are some important references, some may be useful, and here I would like to stop here. If any questions are there, I will be very happy to answer or address. Okay.
Sir, what is about the core size of the matrix heat exchanger?
Core size. What do you mean by core size?
Overall dimensions.
Overall dimensions. Okay. It depends on the mass flow rate. Very common sense. Out of common sense, you can tell. If you have the higher mass flow rate, definitely size of the heat exchangers will be high. Now, if you are talking of a rectangular size heat exchangers, this L by H, that is that the pin height, is a very critical parameter. If H is high, you do not get high effectiveness. We try to make the H as small as possible. In turn, you have to increase the other side, so that with a small H and large length, we have the heat exchanger. That is very odd shaped heat exchanger, but that is the reality. You should have small H and larger in the other side. width of the plate should be larger.
But sir, if we increase flow depth, in that case pressure drop also increases.
Of course, it has to. For the same heat exchanger, if you do not change the heat exchanger size, the pressure drop will increase. Pressure drop will increase. Okay. When another issue is that if you have a high pressure fluid, that time you cannot have even this type of design with a small H and longer in this other side. That design also is not possible. Why? Because if you are going for a larger in this side, the high pressure will not hold. So therefore, you have to go for multi-channel square multi-channels. Small square will hold the high pressure, and similarly nearby another small square that will hold the low pressure. So that design is being done. In fact, one of the heat exchanger I am designing for ISRO, that is cooling of gaseous helium by using liquid hydrogen. So gaseous helium, that pressure is 220 bar. 220 bar and flow rate is about 100 grams per second. Such a large flow rate, and this, but we are able to work it out by using a very 2 centimeter by 2 centimeter channel, 2 centimeter by 2 centimeter, 20 mm by 20 mm, and about say 49 channels, such channels. Out of 49, half of it with for hydrogen and half of it for helium. That is how we are managing it. Okay. 49 का half नहीं होता है, that we have to arrange it. Still it is work is going on. So yes, if for any fluid it can be done. Only thing, you know, I will tell you, aluminum brazed plate heat exchangers, that's plate fin heat exchangers, very easy to fabricate. For example, because you can easily braze it from outside. Okay, for that such a sophisticated system is not required. But you look at the compactness. Aluminum brazed plate heat exchangers can go up to 2000 maximum meter square per meter cube, but this is up to 6000 meter square per meter cube. Want to make it? Yes, you are. I mean, you are getting it. That's all. Okay. So if and also it is manufacturing is very costly, because you need a hot press unit which will accommodate this such a large size heat exchanger. So the one heat exchanger I am telling you, that will require about say 25 centimeter by 25 centimeter vacuum chamber. What we have in natural in our center and also in other laboratories, you will find about 15 centimeter by 15 centimeter by 15 centimeter. But what you need is about 25 centimeter by 25 centimeter and to an height of about say 300 centimeter or I'm sorry 30 centimeter. It's a large capacity. So their cost will be multiplied. About say each such a unit will cost you around something like 1.5 crore to 2 crore. Okay, so that cost involves a lot. Okay, so anything else? Anything else? Any questions? And not only that, my email address is there. I hope you can go to our IIT website and find out my email address from there, and you can contact me. I will try to help you out. So far as heat exchanger point of view and heat transfer point of view, I teach cryogenic heat transfer, I teach cryogenic rocket propulsion also, and I also take class of cryogenic heat transfer laboratory. So heat transfer related issues you can discuss with me. I will be able to help you, be it convection, be it conduction, or be it radiation. Okay, so you can contact me. I will help you out. I will give you some guidelines how you should go about, and I hope it will be useful to you. Okay, so I thank you very much for your kind attention and hearing to me. Okay, I hope I have not made you much bored, but still it is my pleasant duty to talk before you, or maybe I am really enjoyed it. Okay, thank you very much.